Cool.
Oh, you figured it out?
Yeah.
Yes.
Okay, because supposedly there's one. Oh, yeah.
Okay.
Thank you.
Hello, everyone. Today we are going to talk about a paper that studies symbolic regression using a transformer. Lots of cool things about this paper, also lots of interesting limitations. I hope we discuss those. I'll try to see it in a way so I can also see the room, because we also have a room here. Today is in person. Okay, so the paper was published at ICML this year, and it's one of those works that doesn't necessarily have a lot of new theory behind it, which is unusual for ICML, but the problem they are solving is actually really interesting, which means it was a spotlight presentation. So the title says Deep Symbolic Regression for Recurrent Sequences. We'll discuss what symbolic regression means. Basically, the idea is that we are given a sequence of numbers, integers or floats. We want to find a formula that describes it. So the contribution of this paper is finding a recurrent formula, which has not been done before. Okay. So we'll start with a problem setting, the main contributions, a bit of related work, and then we look at the method and lots of experiments. That's the best part. They did a lot of experiments. Okay. As I said, the problem is about finding recurrent formulas to describe a given sequence. So here we can actually, a few examples. Like those formulas can be quite weird looking, right? Like there is this one example here that depends on n, on the previous sequences, complicated functions. But basically, they develop a method that can learn this. So the main contributions is that this paper presents a way to learn recurrent formulas. And usually, these sort of problems are solved by predicting the next few numbers, right? If you do it in Mathematica or any other software, you usually, well, first in Mathematica you can find the formula, but that's a different approach. But usually the best performing algorithms in this sort of setting try to predict the next few numbers. So you give 10 numbers, question is what are the next 10, right? It's like an interview question also. But here we are trying to find the formula because, well, if you have the formula, we can predict as many numbers as we want. It's more powerful. Well, in theory, because we will see that there are limitations. Because first of all, what does it even mean to find a formula, right? How do you test it, that you found an accurate formula? The other problem is there may be infinitely many formulas, and there are. So how do you choose?
One thing that they say right in the beginning, which I underlined, was like, I could kind of see this is true, but I would like to know if anyone has the exact answer or the actual answer. Says that a recurrent sequence is a general formulation of a non-recurrent sequence.
What?
Yeah, it says that. It says recurrent relations provide a more general setting. Oh, actually, they say that later. Never mind. We can go to it later.
Okay.
But I was like how is that the case? It says although this includes non-recurrent.
They are saying that the recurrent setting is more general because you can assume there is no zero level recurrence and then not a recurrence. That's why they mean it's more general to formulate as a recurrence.
But I guess I don't necessarily think that's true.
I was saying for a fixed length pattern. So a non-recurrent pattern of a million will long. But if you open it up to the fact that it repeats, then that's a more general situation.
Maybe that's it.
But if it's not recurrent, then it only depends on n whatever n is. That is just a formula. No? It's just not.
So I was thinking you have a function with an infinite domain that's non-recurrent. That actually seems like more complicated to learn function that is recurring.
Hello.
That's actually been done more than this.
Yeah, this has been done, but the way I understand is they're presenting as if we're doing a more general problem because we are doing recurring relations as opposed to non-recurring relations, which are a simplification of it.
Yeah, but non-recurrent just means that the difference equation is just a function that is not depending on the previous person.
So if your function is just sine x or sine n,
So then you just
Then-
add another dependency
Yeah.
essentially.
Exactly,
Okay,
yeah.
okay, makes sense.
I think that's what I mean.
Yeah.
Cool. And they also do experiments to test the model out of domain. That's actually pretty interesting. So they discuss it at the end, which means when you train your model, you train it for specific functions. But then they test it on functions that have not been used in training. And we will see that sometimes it's even better, but obviously we lose a lot of accuracy, which because it's a very hard problem. But on the plus side for this paper is that other methods are not much better. So it's like, it's still fair. Okay, so related work, AI for maths. There has been work, especially recently, trying to use machine learning to find theorems, to find formulas. They've cited a few papers here. This one is, I think, was from DeepMind. Pretty cool paper. From last year. I had a quick look, quite interesting. They basically use ML to discover new theorems and formulations. That's really cool. Maybe we can do this other paper next time. Also, there is a second paper after this when they fix some of the limitations. Maybe we can also do that. Anyway, let me skip this table for now. Let's look at the related work first. And then they also say, well, there are two ways, as we said at the beginning. You can, given a sequence, predict the formula, but you can also, given a sequence, predict the next elements. So here we are doing the symbolic case, which is finding the formula, okay? Which is supposed to be more powerful. And this is a pre-training based approach, which means we train on a huge number of data points, in this case, generated data points based on simulations. And then we test on a similar data set, which is the usual setting for pre-training, right? If you pre-train a model on Wikipedia for a language model, then when you use a language model, it's pretty much same text. But then they also do experiments for out-of-domain formulas. Okay, a bit of they formulate what a recurrent sequence means, and then, as we said earlier, they argue that it's a more generic setting, and then they study all the cases for integers and floating point numbers. Here in this table 4, they basically define all the functions they used, absolute value, square root, and so on, ReLU, sine, and so on for integers. And for floats, the list of numbers is larger because you can do more operations on floats. Because for an integer operation, you want to have only integer divisions, right?
How would the square root define one integers? If you
No, this is not square root. This is square. There's a square root. My understand. It's just square. Square root is for floats. Also, it's important that we define unary and binary operations, because unary takes only one input, plus minus sign, or absolute value and so on. But binary is with 2 elements, because when they discuss the notation, this matters because we will build a tree actually. Right? We build a tree, and then it's a unary binary tree. There is another paper that studies those in more depth. I marked it over here. Maybe it was this paper, one of those. Basically, the idea is that you build a tree. Each node in your tree is either a unary element or a binary, and that defines your expression. And basically, you have to rewrite the expression in Polish format, which means you put the operator and then the values. Okay. There are a few examples here. I think we can have a look.
Imagine if we were taught how to write an expression that way instead of how we're taught. It would be very interesting.
Confusing.
But it wouldn't be confusing because we would know how to read it. We just don't know how to read it easily now. But I like it more because you don't have to use parentheses.
Well, you use parentheses everywhere.
What's an example? Okay, they have an example.
Yeah, I can find one. Maybe I found the example in the other paper. I can write here for the people who are watching. Yeah, then we can find some here. I guess that matters. Actually, doing the presentation, Spotlight, they spend more time on the formulation. I guess you just do like a plus and then you prove A, B, right?
Well, you don't put you don't have to put the parentheses though.
Yeah, it's just a sequence. Yeah, because yeah, exactly. I mean, it's a hub, right? Yeah. Or you do like a sign and then you do X, right? Okay, no mark. Okay, so well, basically, you can build on this, and then you can do like sign plus A B, right? Because then you do the sign as an A plus B. Yeah, and then you can build up the whole sequence. That's why it becomes recurrent, because they are recursive. Good.
Geovaluing it from right to left. So
What?
You change it into reverse function, actually value.
Yeah.
So there's only one way that we can perform the operation, because it's wherever you have like the first two numbers is the first operation, basically.
Yeah.
And over here's an example.
And then we can also draw the how you make a tree.
See, like,
Because then you can have this plus tree. This is a binary, and then you would have a sign here. This is unary. And then you end up building the whole thing, and your inputs are here. And then
you have
to see this.
like more outputs, right? Because in the class on the left hand side, you could have not just a sign, this is how I understood that each tree has as many nodes as you have operations available to.
Oh, then you expand, yes. Yeah, because that's how you end up expanding the
Yeah, but I'm
expression.
not quite sure.
Yeah.
On the sampling is quite interesting, right?
The sampling
Yeah, when they sample the
to generate data set.
Yeah.
So yeah, the sampling. Maybe I go back and discuss that. Yes, that's actually important because you can have so many options. That's why they argue that it's that there is very low chance of data leakage because there are so many options when you sample. There are so many possibilities. It's very unlikely that you will have the same sample both in the training and test sets.
But they still argue that they parameterize these trees, right? So they say in distributions when the parameters are the same as.
Yes. So out of domain, they say domain, I think basically means you use an operation to generate numbers that have not been in your training set. So
yes, the tree can be deeper.
Yes.
Yeah.
And
just using different, like you have instead of sign, having like, I don't know, what's a function that.
Oh, they have these funny functions.
Yeah, they just have random functions that aren't in there.
Let's scroll down.
Binary operators. Like
So
maybe times pi.
Oh yeah, pi is the best one. Yeah, they use pi, but also so there are two ways to. Let's not jump. There are a few ways you can go out of domain. You can use pi, but you can also use functions that are not in the training set, like functions like.
One thing they say in the method at the very beginning is they say, under this form, the problem is undetermined. Basically, what you mentioned before, that you can have a sequence that can have an infinite number of different recurring sequences, like symbolic representations of the sequence. And then it says, given a finite number of input terms and an infinite number of recurrence relations exist. However, in practice, one would like the model to give us the simplest possible solution following Occam's principle. This is generally ensured by the fact that simple expressions are more likely to be generated during training. So, I guess I was about to say, I don't feel like there's anything in their methodology which enforces simplicity as a method.
Because when I read the sentence, I was expecting some sort of regularization in the uniform sparsity or whatever. But they're like, no, the way we train, it seems to work.
In fact, they mention it again, a bit further down there, like, you could come out with 1 plus UN minus 1.
Yeah.
You know,
I argue that the finite depth of the tree also helps by giving it simple, right?
They have what, 10? They have 10? Something. But
There was also a question how actually it works internally, how the machine.
The depth of the tree is 10, the number of operations is 10.
was the depth 10? Was also 10, no? Maybe.
You can have something of depth 10, but it's 10 or less, I guess, because you have something that's like depth 5. Or,
Yeah.
Yeah.
Because you sampled that also.
Yeah.
Okay.
so they're basically trying to construct the sequence like this,
Mhm.
and then they evaluate it.
Well, they construct millions of sequences and they train a model to tell you what the symbolic expression is for it.
Can we get there?
Sorry,
We're jumping forward.
got it.
Because okay. Examples of functions that we mentioned before, I found those in this table, like Bessel functions and Catalan. Didn't know what these were, but some functions. Yeah. So those are functions that are not in the training set, but then they use them for approximation tests.
But these are just functions that are generating the expression, right?
Yes, for testing.
They don't.
So you use them to generate expressions, and then you test them that using the model you have trained. So your model gives another formula with functions it knows that approximates it.
Yeah.
So the model has access to the raw functions like sine, and cosine and so on.
They have another cool example here, how that actually works nicely, because I think it's later, but so if you try to approximate 0.33 times x, it can't do it because there is a factor in front. We don't know how to do that, right? So you would think doing x over 3 would work because you can divide in 3 is in the range. Well, actually, model finds
Minus cosine.
I think minus cosine 3, minus cosine 3 times x, which
Divided by 3.
divided.
That's what they say.
No, okay, because if you do cosine 3, it's close to 1, but 0.98 something divided by 3 gets very close to the 0.33. Right? It's like it looks weirder, but it's more accurate. It's quite cool, right? Yeah. Anyway,
But it doesn't have to go against their like simpleness aspect of it.
is what?
Doesn't that go against their sort of simple expression?
Well, it's a better approximation.
I guess
So
it's a trade-off,
simple
right,
means
between, like getting closer to the sequence.
So they don't penalize complexity by itself.
No.
so they say if you have the same approximation error, we want to choose the simplest version.
Well, so their argument is they say this is generally ensured, the argument raised by the fact that the simple expressions are more likely to be generated during training. So they're saying like the synthetic data they're creating to train their model is like teaching the model to find simple expressions. And so
Because the model's quite limited in what it can produce, right? So it only has like access to a small number of functions to build up.
Because you can always, trivial case, you can do plus 0 times 1, whatever. You can always add that, which is in the range of the model, but it shouldn't do it because you don't generate those during training.
Yeah.
Okay. Spoke about these recurrent sequences. We spoke about that also. The method. So we briefly spoke about that also, but we mentioned the symbolic versus numeric differences. Data generation, mentioned that, but let's go through the steps because, well, that's important.
that's the main contribution, in fact, I would say.
Yeah, I agree. Yeah, because otherwise they're using a standard transformer. They actually say we took exactly what was in the attention is all you need paper. Just use that. That's pretty cool.
So how does actually output look like? Is it like a
Sequence of numbers. The output is a sequence of
The
numbers.
output is
Oh no, is a formula. the loss function is the
That's
same.
probably the network will output like a zeros and ones that somehow combine to.
Oh, they have a dictionary. They have a vocabulary,
Yeah.
which they use similar to language model. They end up with a vocabulary. We talk about the vocabulary size, but they use a vocabulary. It's like about 10,000 size
Because, yeah, how do you represent composite functions?
with the vocabulary. Yeah. Okay. So right. So let's talk about the data generation. Then we go into the model part. So we have to sample a number of things. Okay. First, we sample the number of operators between 1 and the max. I think the limit is to 10, but we look at the exact numbers during experiments. But this is not a huge number. Then you sample the nodes of the tree, which are the operators from the list of operators that we defined before, right? So table 4 is up here. So we have for each setting, integer or float, we have unary or binary operators, and then we sample from those. And then we sample the recurrence degree, which is also between like 1 and 10, I want to say, but it's not in hundreds of thousands. Then you sample the leaves of the tree. So basically where it ends, which can be a constant or a probability. Okay.
No, the probability is whether it's going to be a constant or one of the indexes of the degree of the recurrence step.
Yes.
So for example, if your current step was 2, you could either have it being a constant or 0 or 1 or 1 and 2 or whatever the index is.
Yeah.
Or the value of the sequence at.
Yeah, that's what I meant by 0 or 1. So it'd be like the previous number or the one before it.
Or the index.
So actually, this tree is the tree already built because yeah, what is this tree? Is this tree?
I think you're generating the tree.
It's built at the beginning though. With the,
How many
with the operator.
index or previous?
Yeah, because they want you to find a number of operators, right? So the tree.
This is encode the function.
Well, in theory, it's there, right? Because you have a limited number of operators.
Just that the.
But you sample to make an extra.
But this tree must become very, very large, right? You say you have like such a huge space of potential.
Yeah, but I don't think you store it because as you sample, you generate one formula, so it's not.
So you
Written
never
anywhere.
have to build it actually.
No, because it grows exponentially.
Yeah, just because it says sample the leaves of the tree, it feels like they.
I think what they are doing is there is a theoretical tree, and then you sample a path on it, and then you save that one path as one formula. I think so.
This is just ways to randomly generate formulas, right?
Yeah.
This is just that's what that's
Mm.
so that they can get the data.
You wouldn't read the tree. Right?
So this tree idea is from another paper.
Yeah.
They cited the paper earlier. I think this one maybe. I think it's this one of I think there's chart on appeared a few times. One of the papers I think describes the way of defining a tree. Okay. And then next step is to calculate the true recurrence degree. Random distribution. So we also need to sample the initial terms. But this is the degree. And we need to, what does an initial term mean?
I think it's like the minimum number of terms to be able to calculate the next term.
Because you need to see the sequence. If it's recurrent, you say you need to have some initial values.
But that's also random by how many initial we have.
Well, it depends on the recurrence, the degree of the recurrence.
They have D effective, which is the recurrent depth, and then plus L, and L is sample. That's it says in 6.
It's like the Fibonacci sequence, but it depends on previous number, the number before. So you need at least two starting values. But you only know that you need 2 after you know what your recurrence relation is.
Right. So you can do a few more than 2. Or is it?
I think just start step 5 is just like get all the starting terms you need, so that you can sample as many as you want.
Instead of 6 or 7.
So to sample the actual sequence. Right. Okay, fair enough. So because at this point we already have the formula, and then we want the initial few steps to sample the rest. and then we sample the input, which is I think usually again around 10, and then it's like you to generate
the length of the input, right? Because the input becomes deterministic.
Yeah, and then that will become an input to the model. Those elements. Okay. So no, this is interesting. Note that in the last step we interpret the computation. If we interrupt the computation, if we encounter a term larger than 10 to the power of 100, but outside the range of the operators. So basically, sometimes you end up with too large or too small or stupid numbers. Like if you have to divide by 0, you just don't do that. Makes sense. And here are the hyperparameters, the parameters they used for sampling. Maximum degree, only 6 actually. Operators 10. The length can be 30, but fairly small numbers. The probabilities for the constant or index or variable leaf, so all equal probabilities here. And the range is between -10 and 10. But those are just for the first terms, right? Okay. They talk about the limitations. Poor auto-distribution generalization. So we speak about this later when they do the approximation experiments. We mentioned this also, but they say it in front that upfront that there is a limitation here, but that's fair. And then we talk about encodings. This is also cool. Well, I guess also normal. How you encode integers and floats. Basically, you have to choose a base for your logarithm, which means the higher base. There is a trade-off, right? Because if you do 10 base, then your integers, well, you have 10 digits. But if you do higher base, then you have more digits, but you have also smaller numbers. So you have to find the trade-off. And I think they use base 30 to encode integers.
No, they use base 10,000.
Oh yes, that makes more sense. So we end up with the vocabulary of also 10,000. Yeah.
So can I ask one question here? So we've used the trees for producing the formulas that we're going to generate training. We can use those formulas to produce the training data. Now, this is transforming. So this is talking now about the vocabulary we're going to encode the formulas or the sequences, or is it actually, are we doing both? How do you?
So they have separate ones for the sequences and separate for the inputs, which are numbers. Yeah. But the numbers, essentially, they have a multi-dimensional feature vector that's composed of embeddings. Okay.
And then,
so the one that we're talking about now is for integers. Like, what does it look like?
Okay,
yeah. With floats is similar, but you have two parts then, and you also need to save the power of 10. So you put a sign here. You also have to limit how many floating points.
It's called Manisa, and I was wondering, does anyone know where that word comes from?
Well, what word?
Yeah. In Greek it means witch. So that's why I was like, yeah. That's why I was wondering why.
Like the floating point, the floating part.
Yeah.
It's like which question. Yeah, I thought when you said which, I thought you meant which the question. Call it.
Okay. And then we also need to encode the recurrence relation. We kind of gave an example there. If you want to do cos 3x, you do cos multiple 3x, and then you get an encoding there.
So that would be the output, the expected output of the one.
Yes, we are predicting that.
Of course, we wouldn't predict x, right? So instead of x, we would have u -1 and u -3 as tokens.
Well, so there is no recursion here, right, in this example.
Yeah, but if the model would predict an output, right? So it would have a way of saying n, and it would have a way of saying maybe take the value u-1 or u-2. And
Oh, because you have to encode also the index.
yeah.
So like you mean this one?
Yeah.
The generation procedure implies that the recurrence relation is not simplified. No, this is different. No. Yeah, yes.
X doesn't really make sense in this, but actually maybe n if you replace x by n, it would
I think each different operation, and then each like n or u of n or whatever, all of those have their own index in some and you just classify basically which one is in each position, and you're doing multi-class classification as the output of your model. And so that would require you to know
a sequence, right? So you return a sequence of tokens. So actually it's quite interesting about what kind of loss they use in that.
But I think you assume some fixed depth, like your output sequence can have a fixed length of
So you would
this or less.
Yeah, upper limit, not fixed.
Yeah,
You know?
upper limit.
So how does it know when to stop generating the next? So
Probably has well, actually a key component of this is during training how they construct the ends so that they're
And how they separate from the next.
it's like a separator.
because
I mean, input is just a list of numbers encoded as the thing, right? And output would be also just a list of tokens, which is the Polish notation for the formula that it's supposed to be. But then how?
So what it says over here that during training, we generate expressions using greedy decoding. So basically, in each position, they take the max. They assume that the maximum. Actually, they don't need to generate. They're training with cross entropy loss. But never mind. Yeah, we're just training with cross entropy loss.
So they would cross entropy loss in this case would be they have the sequence, and for each position in that sequence, they say either yes, we hit the right formula or we didn't.
Well,
No, I think they evaluate. No, not training. The evaluation is done by sampling. They actually get the next.
by beam search.
They do the next 10 elements and then they compute the error.
Yeah.
But that is evaluation, but that's not for training, right?
Yeah, for training, what they're doing is they're just maximizing the negative log probability of the correct class in each position. And probably if the sequence is shorter than the maximum sequence depth, then the last tokens are just like empty tokens.
Yeah.
Yes.
So they either succeed and because they got everything correct or they don't.
Well, since you're trying to maximize the negative log likelihood, you're just trying to increase the probability in the correct class, but that doesn't, you don't require to do an actual classification for that.
Yeah.
It's operating over the probabilities that are outputted by the model.
Yes. Exactly.
Yeah.
So how does it work? So you assign a probability to each token, and then the probability of the next token is given the series of tokens you already. We have to sample.
I don't think that I guess if you were during training, I think they do it all at once.
So they just run through the tree,
Because the way a decoder works is that you mask out everything from, like, you have in a transformer. If you have 10 points, then it attends to all the points before it. If you have 9, then it attends to all the points before it. So you don't actually have to like sample in order to do the attention, but it's doing attention over the representation within the transformer and not of like the sampled class. So it doesn't actually use the sampled class as part of its input.
How do you assign the probability then to of the right answer to what one says? So how does it work?
You have the right answers when you generate a data set.
Yeah, that's true. But let's say I have my model output. And how do I assign the probability of the correct answer?
Well, because from the input, you have the correct answers, right?
Yeah, sure.
Because when you train, you know the formula.
Yeah.
So you have the correct answers.
Yeah.
So then how do you do cross entropy?
So
they calculate the values that the sequence would make.
I think that's a way. I don't know if that's how they train the model. I think that's how they evaluate the accuracy.
Yes, that's how they do for the evaluation. For cross entropy loss, I don't.
So the transformer tends to like everything out before in the sequence. But when they're trying to, like, if the correct class, if this is 0 and this is 1, and the correct class over here is 1, 1, 0, then it would calculate the cross entropy loss of basically maximizing this class, which would be like basically minus log of 0.1.
But this would mean that the positions are independent, yeah, no, right? Because
Well, so they're not independent because the attention mechanism within the transformer means that all the information that was used to calculate this was also used to calculate this. But during inference, what you actually do is you sample and you feed that in, and then you sample and you feed that in. So you do what you're talking about, but you can't do that during training because sampling isn't differentiable.
yeah, exactly.
And so it's basically you're taking the probability vector as your input for the next one as opposed to the actual class.
But that's going to be sort of also so 0 and 1 would actually be your output dictionary size.
Yeah.
Yeah.
But it doesn't, the way that a transformer works is it doesn't have to be iterative. Like that's the main reason why, one of the reasons why attention is faster than recurrent neural networks, because you don't have to iteratively calculate.
Yeah.
You can do all the calculations at the same time.
Sure.
Yeah.
And then the data that they put into this in training, is it the numbers that are generated from trees or formulas as well? Or we don't know at this stage.
The label is the formula.
The label for, so I was thinking when they were doing language models for the transformers, that there weren't any labels, they just had sequences of data.
Yeah, they've generated sequences here.
And so with the label token, the correct token in any particular place is your label, right?
Yeah.
Meaning for that sequence, the actual formula is blah, 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 blah. You mean for the label, you mean it's the correct token in that location?
You do have labels, yeah, because you generate from a formula which becomes so it's supervised, but it's pre-trained, but it's supervised.
That's okay. Okay.
So the transform actually creates an encoding of your problem. And in inference time, I would sample from the encoding and it would get sequences that more or less all of them should be a good approximation of the problem. And I can also do it in reverse. So I have my encoded state, have a sequence, and then ask what is the probability.
Yeah.
Yeah.
Well,
Yeah.
You do it through this.
Cool.
But I agree that the conditional, like the way that they do it, I guess is it's not taking the likelihood that they're calculating is assuming independence between the tokens, like here. But in terms of the information that's being used to calculate those probabilities, there is that conditional dependency. So it's using, but at inference time, you can do the conditional dependency because you can sample and then that will change the probabilities of everything moving forward.
Exactly.
So you can do likelihood estimation at inference time.
So you mean sampling?
So sample the first token, it would change the probabilities of everything after that. Sample the second token.
But you take your encoder, you rather than sampling the first token, you actually plug in the token you have and ask what's the probability.
Yeah.
Then you force it to make the next prediction, then you like put in the next, and this way, even you might end up with the actual string, which is of course maybe very unlikely to have been ever sampled, but yeah, that makes sense.
Cool. We spoke a lot about training. That was going to be the next step, the next part, so perfectly timed. A few details, part size, epochs, not very interesting, I guess. The interesting thing is they have 5 million training equations and 10,000 for the holdout data set. which is very small, but it's fine.
2%.
Yeah. I mean, you could just generate more, right? I don't see the point, but maybe there is also no difference. Cool. I think the next important thing I wanted to mention is how they measure accuracy. We also spoke about this. You sample the next, let's say, I think 10 or so elements, and then you measure.
Don't you have to first sample your hypothesis?
So you,
Yeah.
I feel you sample the equation and use that equation
Yeah.
to predict the next 10 steps.
Yes, you get the equation, and then you use the equation to predict the
Yeah,
next steps.
But the model itself would not give just any equation, but it gives you a space of equation from which you probably have to sample. I think if you go up one.
Ah, you mean this one? Yes.
That's when, do they use?
I tried to skip it, but yeah, because we have only 5 minutes left.
Yeah.
So I would make this- yes, but yes, yeah, yes.
Yeah.
So we use beam search.
Yeah.
Size 10. And they fit the hypothesis to the part of the sequence that they already have to find which one has the best fit. I don't know how they break ties, doesn't say.
Doesn't matter, probably. Yes. Yes. And then basically they measure the accuracy based on the true value, well, this difference between true and the sampled values. Tau is tunable. We'll actually play with that a little bit in the experiments. Let's actually go to some results. There are lots of population studies, but let's have a look at the results. So tolerance is tau. So our method is symbolic. And then we have integer operations or float. And then they are comparing with the numeric methods, again, integer or float. So obviously, floats are harder because it's a broader space. So you can see the accuracies are lower for floats, but also symbolics are always higher, like the green and the blue. And lower tolerance also means higher accuracy, makes sense. But seems like tolerance affects the.
No, higher tolerance is higher accuracy.
Higher tolerance, higher accuracy, yes. What did I say?
Lower tolerance.
No, I meant higher, yes, thank you. Well, yeah, yes, of course, yes. Number of, but they also do some more studies, some more experiments with how many next steps you predict, how many operators you use, the recurrence degree, and the length of input sequence. This all makes sense, right? For example, if you have more operators, it's a harder problem, so the accuracy goes down. And always, the symbolic methods are better, as expected, and float is harder. This one is interesting. Let's look at this other plot a little bit more. Can zoom in here a bit better. So first, we look at the left one, which is the in domain. Basically, they want to study which sort of operators are easier or harder to learn. As you can see, things like the trigonometry is hard because it's just complicated. Division is also hard, surprisingly. And as always, a symbolic method that we used here is so much more accurate. This is actually very encouraging.
What's the difference between numeric and symbolic?
So symbolic, you try to predict the next, predict the formula.
Yes.
Numeric, you just predict the next 10 elements.
Okay.
Right?
I wonder if the numeric is so much worse for the numeric.
Oh, they actually mentioned that here. I just don't remember, but they do mention it. Numeric is so much worse for.
So I would have thought that
For
numeric for me it's quite rejection.
First, I would say 40% is actually not that bad for this problem.
Maybe because it's out of domain.
No, this one is in domain.
No, polynomial.
But it would still be neural network that trains the numeric coefficient, right?
I'd say it's just the finding formula is not easy. That's all. 40 isn't that bad. I think it's problems. Alexander?
Yeah, I feel like it's also the fact that they're not predicting number, they're predicting like this encoding with the mantissa and stuff, no? The way the number are encoded is not flows. So I guess that's why the prediction is harder. That makes sense?
So because their inputs is like tokens instead of the numbers itself, that's why it might not do so well for the numeric example.
Yeah, that's it. Yeah, kind of thought about good.
Yeah. I didn't think that.
I don't know, maybe.
Yeah. Makes sense, yeah. The other plot is for out of domain. We mentioned what out of domain means, but actually there are a few ways to get out of domain data. One is using things like pi in your equations to generate, because our functions don't know pi, but they can kind of learn to instead of pi to have tangent 1. But then the point is that if you do out of domain, that becomes an approximation. And actually also the symbolic methods are so much better for polynomials.
But
yeah.
For the polynomial, so given the operator you have access, you already have access to the polynomial. So it's not really out of domain, is it?
I think what he's saying is that it's really not out of domain, because if you have like square, then you basically have you can express polynomials with the operators.
Yeah, you got multiplication, addition, everything, right?
Maybe it's too deep. If you have a long polynomial, maybe it's too deep.
Yeah.
But you don't have. Do we have power here? We don't have a power.
But you can
You can do like an exponent. Yeah, you can make an expansion. Yeah.
Or you can do many multiplications. So.
Yeah, we can. Yeah, or you can get an
You can change the base.
expression. Well, so the symbolic one learns polynomials well because it can find the express them, but the numeric one doesn't, right? Is it what we are saying?
Yeah.
Yeah. But these other weird functions are actually perform quite poorly, except they argue that this isn't all that bad. 40% out of domain is actually not that bad accuracy.
It knows these functions purely based on the labels of the training data and the available dictionary there. So.
Yes.
Okay.
I think, yeah. How else, right?
Yeah.
They also do a bit of embedding visualization. This is actually really cool. So they made the TSNE plots for the integer and exponent embeddings. You can see the numbers are so nicely aligned, right? Same here, which is very encouraging. It's like if you plot the embeddings for the numbers, they actually end up so nicely aligned as a sequence.
And that is actually surprising, right? Because the original numbers are tokens, which are not necessarily close in space.
Yeah.
But then you make the TSNE.
But you know, TSNE is a stochastic mapping.
Yeah.
Maybe they try it until they find a nice. Everyone does that, right?
Yeah.
Fair enough. Yeah.
It tries to preserve.
Yeah. No, and it's got some like guarantees about doing so. But it's just that
You will get something that
you'll
looks
get very
quite nice.
different. There's a lot of hyperparameters, which is
Yeah.
you have to know how they change.
Disney is not as scientific. It's a cool visualization, but you can't make scientific judgments based on that.
They're probably saying we don't have enough plots in this.
Yeah.
Let's get some more plots.
Like there are like probabilistic guarantees about convergence of the distance preserving, like for the number of samples you have.
And it sort of preserves, I think, topology, right? So in this case, that the numbers are actually like aligned, that probably is relatively stable. I would think.
Okay, I think that's all. We spoke about the out of vocabulary. They also mentioned this cos 3 and over 3 thing I mentioned earlier for width constants. But also if you add this irrational constants, there's another way of generating out of distribution, out of domain numbers.
How do we add these? You could add them during training time already, or do we?
What do you mean add?
What did you say like E and pi and?
You can put them in the range of numbers. So you can. So normally we have, if you have it's integers, we have all integers encoded between -10 to 10. They're saying maybe you can just put them in the encodings.
As an input.
As in you can generate a sequence, I think, using them, feed that sequence to the
This
model and
minus
see
10
how it approximates those constants.
Yes.
The -10 to 10 is the initial term in the sequence. They sample from -10 to 10, but then they say like we can add these 3 constants in and sample from those as well, and then it's going to be out of distribution.
Actually, the float case, it was also the float case doesn't rely on integers, but about
But they just use these as for the flow cases.
You know the limitation it mentions that it samples the first values from -10 to 10. It says if you sample from outside that, it's really bad.
Yes.
I don't understand why that's the case. Why I can't generalize to seeding from other
Why would it?
integers.
Because you're going from positive 26 like you can vastly in a space. The numbers could just be a magnitude, it just doesn't sit.
I would think that because it doesn't know the function, it doesn't have access to the actual function, but it can't try to apply a function to a value and see what it comes out to. I would think that the model sort of learns, if I put a -10 into an exponential, I'm going to get something that is very close, somewhere in the space. And that,
Do you think it's partly as well, like what we saw with the embedding, it's understood that the encodings of the numbers are numbers. If you introduce new encoding.
So I think one thing is the integers that they encode in the as part of the function. But I think the -10 to 10 is what they sample to see the sequence of numbers, right? I think. But it says if you start, like, let's say you start a sequence at like 5 and then it's a recursive, so you build it. But if you start at like 15, then it's like suddenly it doesn't like it.
it probably would, but you can try to do value related to 15 to the certain number of force number down. You would get something that is so odd because it never has seen such a ratio of numbers that it wouldn't know which function actually sort of.
But the sequence is very different then.
Yeah.
That's actually like I find that's such a huge limitation.
Yeah, but it's not memorizes functional signatures, right?
Yeah.
I'm playing on the language models to get something weird stuff that and it just loses the ball.
So you
It's like essentially you're doing the same thing pretty much 15 where it hasn't seen.
Yeah.
Instance.
it's like
Okay.
don't fuck with me.
Can I mention one other interesting thing? They say, okay, is this applicable for any real life problems? Maybe financial sequence data? I'm like, no, it's all very different. Don't worry about practical applications, just cool math trick. Maybe you can put in Mathematica because they compare with the Mathematica functions quite a bit, and obviously it's so much better. But you can't extrapolate this to use for real life sequences, which I think quite cool.
But they say that the use cases you unwriting for differential equations for extraction.
For future work,
Yeah.
they're saying
this.
yes, exactly. So they mentioned 2 future works after that, future directions. One is handling the arbitrary prefactors, like multiplying by constants at the beginning, and then they have paper covering that part. The other one is making the recursion with discrete version of differential equations. So discretizing differential equations. They are trying to find another application. The differential equations are always useful to find trajectories on them. I'm not entirely sure how this relates, but maybe.
Just a discrete version.
Sample
Yeah.
from
It would be interesting to see if, I don't know if they compare this, but so the symbolic approximation of like best function, for example, how that compares to the actual implementation of best function in like Python, like the numerical approximation that we currently have. I don't know if they,
Usually gets like the leading term, right?
yeah. So that's why, yeah, it will be interesting to see how this also how it works with like chaotic commands, right? For like religiously map, which is a recursion, just creates chaos by applications.
But the relative behavior should be relatively well behaved, right? So that the recursion is quite simple, right?
Yeah, but sort of the logistic map can have loads of points.
Yeah.
For this one specific parameter. So
I would think it would try to do implicitly like diff everything, yeah, and somehow that really reduces complexity.
I mean, it's an NPR problem anyway. So,
Yeah, that's really cool.
Okay. Thanks all of online. I'm gonna start recording and then can continue chat here.
Yeah.
Wait, no, recording is not.